So here we have the schematic of a universal shift register. So as you can see, it consists of four flip-flops labeled A1 to A4 and four multiplexers labeled I1 to I4. So this circuit also includes inputs for the clock like clear and serial inputs for both shift left and shift right operations. So these are the multiplexers, these are the D flip flop, and these A1, A2, A4 stores the output. So let us talk about the flip flops A1 to A4. Each flip-flop is designed to store a single bit of data. So they are all connected to same clock signal which synchronizes the data transfer between the flip-flops when a clock pulse occurs. The data in each flip-flop is passed on according to the selected operation. So when the clock pulse is moving, so the data also changes like this. So next we have the multiplexers I1 to I4. So the role of these multiplexer is to select between the different input data sources based on the operation we want to perform. Each multiplexer has has four inputs, one for the serial input for shifting left, one for shifting right, and one for the current data in the flip flop. So now let us see how the circuit handles shifting operation. So for a shift operation, the data from the leftmost flip flop A4 moves towards the right, and the new bit enters from the serial input designed for the shift left. So conversely, for a shift right operation, the data from rightmost flip flop A1 moves towards the left with the new bit entering from the serial input for shift left. So, this circuit also includes a clear signal, which, when activated, resets all the flip flops to zero. So, this is useful for initializing or resetting the register before starting a new operation. So, to summarize, this universal shift register allows us to shift data or left or right, hold or clear the data entirely. It's an essential building block in many digital systems, from simple storage registers to complex serial communication protocols. So, today in this video, we will learn about some important guidelines for designing systems, separating memory components or registers into individual code segments. To explain this, we will first look at the basic building block of a general synchronous system, often referred to as a sequential system. So here is a synchronous system. So let us start by understanding what a synchronous system is. So as you can see in this diagram, a synchronous system typically has a register and some logic that decides the next state. So this system operates with a clock signal, making it a sequential system. So in general, synchronous systems, there are three key components: a register, which stores the state of the system; combinational logic, which decides the next state based on the current state and inputs; and output logic, which just determines the system's output. So this is the inputs, the output, the combinational logic, the memory. So the output logic can be simple like status of the register or more complex involving various logic. So now let us briefly touch on two types of synchronous systems, that is Moore and the Mealy. So in the Moore system, the output only changes with the state of the register, so which is synchronized with the clock. In a Mealy system, the output can change based on both of the state of the register and the external inputs, regardless of the clock. So, a characteristic feature of synchronous system is the feedback loop, as you can see here, from the output back to the input. So, this feedback loop helps in maintaining system state across the clock cycles. So, now let us understand it with the help of code examples. Now we will define the inputs and outputs of our register. So we will define the outputs, the inputs, the reset, the clock, and the select for our for selecting the mux. So let us start. So here we have declared our module, and this is our parameter, so that our design becomes more scalable and more flexible. So we have declared the clock reset and then the control, the input D and output logic Q. So now we can equate our circuit as shown here. Now we will do the signal declaration of R next and R edge. We have declared our signal here. So why we have taken the bit width n minus 1? So since our register is n minus 1, our output logic is also of n minus bit width. So that is why only our signals also should be same as that. So, as discussed in our previous part of this video, some important guidelines for coding synchronous systems. So, these are the important guidelines. So, according to this, we will be coding. That is why we have created three important segments in our code: the register segment, the next state logic segment, and the output logic segment. Now we will start coding with the register segment. So we have coded the always FF block. So and the posit and the sensitivity list we have updated with the posage clock and the posage reset for the asynchronous reset. And then on the reset, the register will be on reset. The R reg will be set to 0, and if not, it will be changed to the next state. Now we will code the next state logic. So for as we are coding a combinational logic here, so we will use always underscore com, and you can code this segment using a multiplexer also by instantiating it, or you can use case statement also. So or if else also, but here we are using the case statement. So let us understand how this left shift and right shift take place in the universal shift register. So in so r underscore reg is our current state of our register. That is what is it represent the present content inside the register, and here we have excluded the MSB, and we have taken the first bit of the input, and we have concatenated with the current state of the register, and we have assigned it to the next state. So this is how we are doing the left shift. And then let us see how we will do the right shift. So let us understand how this left shift and right shift take place in the universal shift register. So in so r underscore reg is our current state of our register. That is what is it represent the present content inside the register, and here we have excluded the MSB, and we have taken the first bit of the input, and we have concatenated with the current state of the register, and we have assigned it to the next state. So this is how we are doing the left shift. And then let us see how we will do the right shift. So let us understand how we will do the right shift. So let us understand how we will do the right shift. So here is a visual explanation how is the right shift going on. So this is for shifting the left, and this is for shifting to the right. So after this, we have implemented the output logic segment to assign the final output. This is that. And in the next video, we will be implementing the RTL to GDS flow of this universal shift register. So stay